What is the RFD? When we talk about tornado formation, most people think of rotating supercells, wall clouds, and funnel clouds. But there's one critical piece that often goes unnoticed: the rear flank downdraft, or RFD. The RFD is a surge of rain-cooled air that wraps around the backside of a supercell thunderstorm. It's like a mighty shove of wind that pushes downward from high in the storm and then curls around the rotating updraft. This descending air can reach speeds over 60 miles per hour, and it plays a huge role in shaping how a tornado forms, intensifies, or even collapses. Meteorologists often call it the secret weapon behind tornadoes because without it, many funnels would never actually touch the ground. How the RFD forms. The RFD begins when rain and hail inside a supercell start to evaporate as they fall through dry air near the storm's mid-levels. This evaporation cools the surrounding air, making it denser and heavier. Gravity then pulls this cooler air down toward the ground, forming a downdraft. As it accelerates downward, it spreads out when it hits the surface, like water splashing after a stone hits a pond. What makes the rear flank downdraft special is its position and motion. It forms on the backside, or rear flank, of the rotating updraft, the mesocyclone. The interaction between the cold descending air and the warm, moist inflow on the other side of the storm is where the real action begins. That's the boundary where tornadoes are most likely to spit up. The role of temperature differences. One of the most fascinating aspects of the RFD is its temperature contrast. When the air in the RFD is too cold, it can actually choke off the storm's rotation by cutting off warm air feeding into the updraft. But when it's only slightly cooler than the surrounding air, it adds the perfect amount of instability to keep the storm spinning. Think of it like Goldilocks weather science: not too cold, not too warm, just right. That just right temperature difference creates the best environment for a tornado to touch down and stay on the ground. Researchers have found that many of the strongest, longest-lasting tornadoes are associated with RFDs that have a moderate temperature deficit, around 3 to 6 degrees Celsius cooler than the surrounding air. The RFD in tornado genesis. The RFD isn't just background turbulence. It's often the final trigger that helps a tornado form. As the RFD wraps around the mesocyclone, it tightens the rotation near the surface, concentrating angular momentum like an ice skater pulling in their arms. This narrowing rotation can suddenly cause a visible funnel to appear and extend toward the ground. At the same time, the RFD's outflow boundary lifts warm, moist air into the base of the storm, fueling the updraft even more. When those two processes meet, the inflow rising and the RFD wrapping, you get a self-reinforcing cycle that births a tornado. The visual signs of an RFD. Storm chasers often watch for specific visual clues that indicate an active or developing RFD. One of the most recognizable is the clear slot, a bright rain-free area that forms near the wall cloud on the backside of a supercell. That clear slot is basically a visual marker of the descending dry air in the RFD. When you see it forming, especially along with a tightening wall cloud, it's often a sign that the storm is about to produce a tornado. You might also notice strong, dusty winds wrapping around the storm's base, or a sudden change in wind direction and temperature as the RFD sweeps through. Chasers describe it as a gusty rush, followed by a sudden drop in temperature, a signature of rain-cooled air descending rapidly. The dual personality of the RFD. Here's where things get interesting. The RFD can be both a creator and a destroyer of tornadoes. When balanced correctly, the RFD helps concentrate rotation and sustain a funnel. But if it becomes too strong or too cold, it can cut off the tornado's supply of warm air and cause it to dissipate. In some cases, you'll see a powerful tornado form, then suddenly rope out and vanish, often because the RFD surged too forcefully. That makes it one of the most unpredictable factors in storm dynamics. Meteorologists constantly debate how much RFD strength is just right. Too weak and no tornado forms. Too strong and the storm suffocates itself. The RFD and multiple vortex tornadoes. Some of the most dramatic tornadoes ever recorded, like the 2013 El Reno tornado, were influenced by complex RFD interactions. When the RFD wraps unevenly or collides with secondary downdrafts, it can create multiple vortices within one larger funnel. These subvortices spin at incredible speeds and can cause localized damage far worse than the central funnel itself. The interaction between the RFD and these smaller circulations is still a significant topic of research. Doppler radar scans often reveal that these internal vortices are born right where RFD air meets the storm's inflow boundary. What radar tells us about the RFD? On Doppler radar, the RFD shows up as a region of strong outbound winds behind the mesocyclone. As the radar beam hits raindrops moving away from the radar site, it detects a sudden velocity difference, red for outbound and green for inbound winds. That color couplet helps meteorologists identify where the RFD is wrapping around and tightening the rotation. Advanced mobile radar units, like the Doppler on wheels, have helped scientists see just how dynamic the RFD really is. High-resolution scans often show multiple pulses of descending air, shifting temperatures, and bursts of rotation, a chaotic ballet that defines each tornado's unique behavior. Field research and discovery. Since the 1990s, scientists from programs such as Vortex and TORUS have been studying the RFD in real time using mobile radars, drones, and instrumented vehicles. One famous moment came during the 1999 Vortex project, when researchers successfully measured temperature and wind differences inside an RFD for the first time. They found that small-scale changes in humidity and air pressure could dramatically influence whether a tornado formed or failed. These field missions are dangerous, often placing teams right next to developing tornadoes. But their data has completely changed how we understand RFD dynamics, turning what was once a mysterious downdraft into one of the most studied features in severe weather science: the human connection. The RFD also plays a direct role in tornado safety and forecasting, because RFD winds are often the first strong gusts people feel before a tornado hits. Recognizing them can provide crucial seconds of warning. If you suddenly experience a sharp temperature drop, swirling winds, and a rush of cool, dry air, that could mean the RFD is wrapping around and a tornado may be seconds away. For meteorologists, tracking how the RFD evolves helps refine warnings and radar algorithms, potentially saving lives in areas hit by sudden tornado outbreaks. Why the RFD still puzzles scientists. Despite decades of study, the RFD remains partly a mystery. It's difficult to measure directly because it's wrapped inside violent storms and constantly changing. The exact mix of temperature, humidity, and wind shear that creates a tornado-producing RFD is still debated. Computer simulations show that minor differences, as little as 1 degree Celsius in temperature or 5 miles per hour in wind speed, can determine whether a tornado forms at all. That level of sensitivity makes the RFD one of the most complex and unpredictable pieces of weather science today. The RFD's legacy in tornado research. Ultimately, the rear flank downdraft has changed how we think about tornadoes. It's no longer seen as just a side effect of a storm, but as a central character in the drama of tornado genesis. Understanding it has helped scientists improve radar interpretation, forecast accuracy, and our overall understanding of storm physics. Every new storm provides another opportunity to study how this invisible powerhouse shapes one of nature's most violent forces. The RFD might be hidden, but it's the secret weapon behind almost every tornado we've ever witnessed.